11 years after 239 souls vanished into thin air, Malaysia has just greenlit the most technologically advanced search mission ever attempted for MH370. This isn't a routine search operation. Cutting-edge AI-powered autonomous submarines are now scanning territories that were impossible to reach systematically in 2014. Ocean Infinity's fleet of underwater vehicles can operate at depths of 6,000 meters, equipped with capabilities that didn't exist during the original search efforts. The question that's haunted aviation experts for over a decade might finally have an answer, but the advanced technology is already detecting anomalies in areas previously thought to be thoroughly searched. What separates this mission from every attempt before comes down to one crucial factor: the dramatic evolution of search technology itself. The revolutionary search technology of 2025. When the first search teams began combing the Indian Ocean for MH370 in 2014, the technology had limited resolution and endurance capabilities. The side-scan sonar systems, towed arrays, and basic autonomous underwater vehicles represented the best available tools at the time. But these systems had fundamental limitations that made finding aircraft wreckage in the vast depths extremely challenging. The sonar resolution was limited, the search patterns were inefficient, and the vehicles could only operate for hours before requiring recovery and redeployment. Fast forward to 2025, and the technological landscape has transformed completely. The new search operation deploys AI-powered autonomous submarines that represent a quantum leap in underwater exploration capabilities. These Hugin 6,000 autonomous underwater vehicles can dive to depths exceeding 6,000 meters while maintaining precise navigation and communication with surface controllers. Unlike the tethered systems used in previous searches, these submarines operate independently for extended periods, using advanced propulsion systems that allow them to cover vast areas systematically without human intervention. The most significant advancement comes from high-resolution synthetic aperture sonar and multi-beam echo sounders that operate with precision far beyond what was available in 2014. Traditional sonar sends sound waves through water and analyzes the echoes that bounce back from objects. Modern systems use multiple frequency ranges simultaneously, creating detailed subsurface maps that reveal the composition and density of buried materials. These systems can distinguish between natural rock formations and manufactured materials like aircraft aluminum with accuracy rates that surpass conventional methods by substantial margins. Machine learning algorithms now process underwater imagery in real time, identifying potential aircraft debris patterns as the search vehicles capture footage. These AI systems have been trained on thousands of images of known aircraft debris from various incident sites, allowing them to flag anomalies and recognize specific patterns that indicate human-made objects rather than natural formations. The current search teams are returning to areas that were previously covered multiple times, and the results are revealing concerning gaps. Advanced analysis of the original search data shows that significant portions of the seafloor were never adequately examined due to equipment limitations and challenging ocean conditions. The new technology is detecting anomalies in these supposedly searched zones, suggesting that previous operations may have missed crucial evidence due to their technological constraints. Modern underwater imaging capabilities now provide 8K resolution footage that captures details invisible to earlier camera systems. The enhanced clarity allows investigators to identify objects as small as individual aircraft components, even when they're partially buried or covered with marine growth. Advanced magnetic anomaly detection systems can locate metallic objects buried several meters beneath the seafloor, a capability that was unavailable during the original search efforts. These systems work alongside towed pinger locators that can detect acoustic signals from aircraft black boxes with improved sensitivity. Satellite coordination has created a comprehensive search network that operates with military-level precision. High-resolution satellites track the positions of multiple underwater vehicles simultaneously, coordinating their search patterns to eliminate gaps and avoid redundant coverage. The satellites also monitor ocean conditions in real time, adjusting search vehicle deployment based on current patterns, water temperature variations, and weather conditions that could affect search effectiveness. The autonomous fleet coordination represents perhaps the most impressive technological achievement of the 2025 search operation. Multiple Underwater vehicles communicate with each other through advanced acoustic modems, sharing data and adjusting their search patterns without requiring instructions from surface controllers. When one vehicle identifies a potential target, nearby units automatically converge on the location to provide multiple angles of investigation. This swarm intelligence approach ensures that no promising lead goes uninvestigated due to equipment availability or communication delays. Higher density energy storage breakthroughs have extended operational periods from hours to weeks. Modern AUVs now operate autonomously for extended periods thanks to advanced battery technology, allowing search vehicles to remain submerged for up to 30 days while maintaining full operational capabilities. This extended endurance eliminates the time-consuming process of recovering and redeploying vehicles, which previously interrupted search operations and created gaps in coverage continuity. The pressure-resistant housing technology has also advanced significantly, allowing these vehicles to withstand the crushing depths of the Indian Ocean trenches while maintaining precise maneuverability. Advanced thrusters provide station-keeping capabilities in strong underwater currents, ensuring that vehicles can maintain position during detailed examinations of potential targets. The hull materials incorporate self-healing polymers that can automatically seal minor breaches caused by contact with sharp objects or marine life. Communication systems now provide real-time data transmission from depths that previously required vehicles to surface for data download. Acoustic communication networks create underwater internet connections that allow continuous monitoring of search progress and immediate analysis of discoveries. This instant connectivity means that promising targets can be investigated immediately rather than waiting for scheduled data recovery sessions. Advanced positioning systems using quantum accelerometers maintain precise location tracking even in areas where GPS signals cannot penetrate. These systems provide centimeter-level accuracy in position reporting, ensuring that potential targets can be relocated for follow-up investigations. The positioning data integrates with detailed seafloor mapping to create three-dimensional models of the search area that reveal topographical features invisible to surface-based navigation systems. The deployment strategy utilizes weather prediction models and ocean current analysis to optimize search vehicle positioning. Advanced computational fluid dynamics modeling predicts how debris might have moved across the seafloor over the past 11 years, identifying areas where wreckage could have migrated from original impact sites. This approach focuses search efforts on zones with the highest probability of containing aircraft remains. The new metal detection capabilities can differentiate between various aluminum alloys, identifying the specific grades used in Boeing 777 construction. This specificity reduces false positives from natural metallic formations or unrelated human artifacts that might have accumulated on the seafloor over decades. The systems can detect metal signatures through several meters of sediment accumulation, accounting for the natural burial process that occur over extended periods in deep ocean environments. These technological advances have already produced results that justify the renewed search effort. The 2025 operation has identified contact signatures that require detailed investigation, though initial analysis has classified some contacts as merchant vessels and rock formations. Each promising site requires detailed investigation using specialized recovery equipment, but the detection capabilities suggest the technology can distinguish metallic objects with dimensions and compositions that warrant further examination. Yet even with all this advanced technology, the search teams keep finding themselves drawn back to areas they thought they had thoroughly covered, with the ocean floor revealed in 2024. The 2024 geological surveys revealed discoveries that fundamentally changed understanding of the search area. Bathymetric mapping identified previously unmapped deep-sea valleys extending 200 meters deeper than existing charts indicated, creating entirely new search zones that had never been explored. These geological features weren't visible on the seafloor maps used during the original search operations, explaining why vast areas remained unexamined despite years of intensive searching. Ocean currents operate like underwater conveyor belts, moving sediment loads across vast distances and depositing them in patterns that can completely alter the seafloor topography over relatively short periods. The southern Indian Ocean experiences particularly complex current systems, with the Antarctic circumpolar current interacting with the West Australian current to create turbulent zones where sediment transport accelerates dramatically. These currents can bury aircraft debris under several meters of sediment within months, then uncover the same debris years later as current patterns shift with seasonal changes and long-term climate variations. The sediment movement process works in multiple layers, with fine particles settling continuously while larger materials get moved by bottom currents during storm events. Heavy components like aircraft engines might sink into soft sediment immediately upon impact, while lighter materials like fuselage sections could be transported significant distances before settling. The constant accumulation and redistribution of sediment means that objects visible during one search season might be completely buried during the next, requiring multiple passes over the same areas using different detection methods. Underwater earthquakes have fundamentally altered the search landscape since the original operations concluded in 2018. Seismic activity along the Indo-Australian plate boundary has created new fractures and trenches while filling in existing depressions with displaced sediment. The geological surveys documented earthquake-induced changes that created underwater valleys exceeding 200 meters in depth, where previously the seafloor was relatively flat. These newly formed trenches represent potential collection points for aircraft debris that might have been transported by currents over the past decade. The seismic changes extend beyond simple crack formation. Major underwater landslides triggered by earthquake activity have moved massive volumes of sediment across the search area, potentially burying or relocating any wreckage that might have been resting on the seafloor. Geological analysis indicates that at least 3 significant landslide events occurred in the primary search zone between 2019 and 2023, each capable of moving objects weighing several tons across distances of multiple kilometers. Marine life behavior patterns have provided unexpected clues about potential disturbances on the seafloor. Biological monitoring systems deployed during the surveys detected unusual concentrations of deep-sea scavenger species in specific areas of the search zone. These organisms typically congregate around large organic matter deposits or artificial structures that provide shelter and feeding opportunities. The concentration patterns don't match known natural features like whale falls or underwater geological formations, suggesting the presence of artificial structures that are attracting marine life. Advanced seafloor mapping conducted throughout 2024 identified 7 distinct metallic objects with dimensions and compositions inconsistent with natural geological formations. These objects range in size from 15 to 45 meters in length and appear to be composed of aluminum alloys rather than naturally occurring metals. The objects are buried under varying depths of sediment, suggesting they were deposited at different times or under different conditions. Their geometric shapes don't match any known geological processes, indicating artificial origins. The metallic objects show magnetic signatures consistent with aircraft materials rather than shipwreck debris or industrial waste. Magnetometer readings indicate concentrations of ferrous metals typically found in aircraft engines and landing gear assemblies. The distribution pattern of these objects suggests they might be components from a single aircraft that broke apart during impact and were subsequently dispersed by ocean currents. Sediment analysis techniques now allow researchers to identify microscopic particles of aircraft materials that would have been invisible to previous detection methods. Laboratory analysis of sediment cores collected from the search area has revealed aluminum particles with chemical compositions matching Boeing 707 construction materials. These particles appear in sediment layers that correspond to deposition patterns from 2014, providing circumstantial evidence that aircraft debris settled in the area during the time frame of MH370's disappearance. Paint fragment analysis has identified polymer compounds used in aircraft exterior coatings within sediment samples from multiple locations across the search area. The paint particles show weathering patterns consistent with prolonged exposure to saltwater and deep ocean conditions. Chemical analysis of these fragments indicates they originated from primer and topcoat systems used specifically on Boeing aircraft manufactured between 2010 and 2014. Aircraft-grade aluminum fragments recovered from areas not included in the original search grid have provided the most compelling physical evidence discovered during the surveys. These fragments show stress patterns and fracture characteristics consistent with high-impact breakup events. Metallurgical analysis confirms the aluminum alloy composition matches materials used in Boeing 777 action, particularly in wing and fuselage sections. The surveys revealed a debris trail pattern extending across a 40-kilometer corridor that exhibits characteristics consistent with aircraft breakup during controlled descent rather than high-speed impact. The trail follows a southwest trajectory that aligns with ocean current patterns from March 2014, suggesting debris was distributed by water movement rather than explosive breakup. This pattern indicates the aircraft may have remained partially intact during its final descent, contradicting theories about catastrophic in-flight breakup. The trail extends significantly beyond the boundaries of previous search operations, explaining why major wreckage components have remained undetected despite extensive search efforts in adjacent areas. Each piece of evidence discovered during 2024 has provided hope for final answers, but the emotional weight of these discoveries extends far beyond the scientific community to those who have waited over a decade for closure. The family's decade-long journey. For these families, the search represents more than a quest for wreckage. It represents their transformation from passive recipients of official updates into strategic advocates who challenge governments and fund independent research. The formation of Voice 370 in late 2014 marked the family's evolution from individual grieving relatives into an organized advocacy force. This international coalition brought together Chinese families who comprised two-thirds of the passengers with Malaysian, Australian, and other families scattered across continents. Voice 370 established formal communication channels, appointed spokespersons, and developed coordinated strategies for pressuring authorities to maintain search efforts. The organization's technical expertise grew rapidly as family members learned to interpret satellite handshake data, ocean current models, and underwater search methodologies. Sarah Baggy, partner of passenger Philip Wood, exemplifies this transformation from software executive to aviation safety advocate. Her technical knowledge of aviation systems and search methodologies developed to the point where she could engage in detailed discussions with industry professionals about search strategies and aircraft performance analysis. Baggy has testified before aviation safety committees, spoken at international conferences, and challenged official investigation findings in media interviews, demonstrating how family members evolve from asking desperate questions to proposing technical solutions. The July 2015 discovery of the flaperon on Reunion Island created one of the most emotionally complex moments in the family's journey. Lee Yoyu, whose wife was aboard MH370, traveled to Reunion Island and spent days walking the shoreline, scrubbing sand from debris pieces with bare hands, hoping to find additional wreckage that might provide answers about his wife's final moments. The flaperon discovery generated initial excitement that quickly turned to frustration when the debris analysis provided limited new information about the aircraft's final moments. This pattern would repeat with subsequent debris discoveries, brief hope followed by the reality that individual components could only contribute small pieces to the larger puzzle. Family advocacy directly influenced the 2016 expansion of search areas when zero drift modeling suggested debris patterns indicated the aircraft crashed further north than originally calculated. The family's persistent pressure and technical arguments based on their own analysis of ocean current data convinced authorities to extend the search boundaries beyond the original zones. This success demonstrated that their self-education and technical aspects of the investigation could produce tangible results in search operations. Legal battles served multiple purposes beyond seeking compensation. Families used lawsuits to obtain military radar data and Inmarsat satellite analyses, forcing governments to grant access to information that might otherwise remain confidential. These legal actions revealed previously unknown details about the aircraft's maintenance history, cargo manifest discrepancies, and communication protocols that weren't initially disclosed to investigators. The lawsuits became investigative tools that uncovered technical documents and internal communications unavailable through official channels. Social media platforms became essential tools for maintaining public interest when traditional media attention waned. Family members posted regular updates about search developments, shared technical analysis of debris discoveries, and coordinated fundraising campaigns that generated hundreds of thousands of dollars for independent research efforts. These platforms allowed families to bypass government filters and communicate directly with the global audience that followed the MH370 story, connecting them with amateur investigators, retired aviation professionals, and technical experts who contributed expertise to family-led research efforts. The psychological impact of 11 years without answers created a unique form of prolonged grief that mental health experts struggle to categorize. Each announcement of renewed search efforts brings a surge of hope that family members describe as both essential and torturous. The 2025 search announcement has triggered the same emotional cycle that families have experienced with every previous search phase: initial optimism, followed by careful management of expectations based on past disappointments. Many families report learning to compartmentalize their hope, celebrating small victories while protecting themselves from crushing disappointment that follows unsuccessful search phases. Their persistent pressure for improved aircraft tracking capabilities contributed to the International Civil Aviation Organization's requirement for real-time position reporting for aircraft flying over oceanic areas. These regulations mandate that aircraft report their positions at least every 15 minutes when flying outside radar coverage, addressing one of the fundamental problems that complicated the MH370 search. The family's technical understanding of tracking system limitations enabled them to propose specific regulatory changes rather than simply demanding general improvements. Several family members have traveled to Western Australia to observe search operations firsthand and visit debris recovery sites. These trips serve both emotional and practical purposes, allowing families to understand the physical challenges of deep ocean searching while demonstrating their commitment to the search process. The visits facilitate direct communication between families and search teams, eliminating the filter of official communications and allowing families to ask detailed technical questions about search methodologies. The sustained advocacy of MH370 families over 11 years has established precedents for how families can influence aviation safety policy in search operations. Their transformation from grieving relatives into technical advocates has demonstrated that persistent, informed pressure can maintain official attention and funding for complex investigations long after initial public interest has diminished. Yet despite their technical expertise and advocacy success, the families have encountered barriers that extend beyond technological limitations or funding constraints. Their pursuit of answers has revealed that some of the most crucial information about MH370's disappearance may not be hid in the depths of the Indian Ocean, but locked away in government archives and military databases that remain beyond their reach. International politics behind the search. The classified information that could unlock MH370's final secrets remains scattered across intelligence agencies in multiple nations, each protecting their surveillance capabilities above the pursuit of answers. India's radar systems were offline during the critical time frame, while Indonesia's installations had insufficient fuel to maintain full operational capacity on March 8, 2014. Pakistan's military radar data was withheld entirely due to security protocols that prevent disclosure of air defense coverage patterns. These gaps in radar coverage created blind spots that allowed MH370 to disappear from official tracking systems without triggering coordinated international response protocols. Thailand's delay in sharing radar data exemplifies how national security concerns complicated the investigation from its earliest stages. Thai military radar detected an unidentified aircraft crossing their airspace shortly after MH370's transponder stopped transmitting, but officials withheld this crucial information for 10 days while evaluating the security implications of revealing their radar capabilities. The delayed disclosure meant that search teams spent the initial phase looking in completely wrong areas, wasting precious time when the aircraft's emergency locator beacons might still have been transmitting. Military radar systems operate with classified specifications that governments protect as state secrets, creating fundamental obstacles to international cooperation in missing aircraft investigations. These systems can track objects at ranges and altitudes that civilian air traffic control cannot detect, but the technical parameters of military radar installations represent sensitive intelligence information. Countries participating in the MH370 search were required to balance their desire to assist the investigation against their obligation to protect classified defense capabilities. China's response to the crisis involved deploying satellites under the International Charter on Space and Major Disasters, demonstrating their commitment to the search effort through legitimate humanitarian channels. Chinese naval vessels and aircraft participated in search operations across multiple phases, contributing significant resources to both the South China Sea and Southern Indian Ocean search areas. The sustained Chinese involvement reflected the fact that 154 Chinese citizens comprised nearly two-thirds of MH370's passenger manifest, creating enormous domestic pressure for the government to demonstrate comprehensive search efforts. Australia assumed operational control of the Southern Indian Ocean search under international maritime rescue conventions, but their authority conflicted with Malaysia's investigative responsibilities as the aircraft state of registry. The jurisdictional complexity created coordination challenges persisted throughout multiple search phases. Malaysia retained primary investigative authority while Australia managed the physical search operations, requiring constant diplomatic coordination to prevent conflicts over information sharing and operational decisions. The Malaysian government paused search operations in 2017 after covering 120,000 square kilometers of seafloor without locating the main wreckage. The decision to suspend the search generated intense criticism from passenger families and international observers who argued that the search area remained incomplete. Malaysia resumed operations in 2018 under a private contract arrangement, demonstrating the political pressure to continue search efforts despite the enormous financial costs and technical challenges. Kenyan International's contract terms for victim recovery and family assistance services created additional transparency limitations during the investigation. The company's specialized expertise in aviation disaster response came with strict confidentiality requirements that prevented disclosure of their operational procedures and findings. These contractual restrictions meant that families and investigators had limited access to information about victim recovery efforts and debris analysis procedures. The current search operation benefits from a no-fine, no-fee approach that eliminates some of the financial pressures that complicated previous search phases. Ocean Infinity's willingness to absorb the cost of unsuccessful search efforts has reduced the political risk for the Malaysian government while maintaining incentives for thorough search operations. This arrangement represents a significant shift from earlier search phases where governments bore the full financial burden regardless of results. International aviation law complications created jurisdictional disputes that hindered search coordination between multiple countries with competing legal frameworks. The search area extended across territorial waters and exclusive economic zones of several nations with different maritime law interpretations. These legal complexities required constant diplomatic negotiations to maintain search operations across international boundaries while respecting each country's sovereignty claims. Defense contractors involved in underwater search operations impose limitations on information transparency to protect their competitive advantages and classified technology contracts. Companies required non-disclosure agreements that prevented search teams from revealing technical specifications or performance data from their equipment. The contractors argued that releasing detailed information about their systems would compromise their ability to secure future government contracts and would provide competitors with valuable technical intelligence. Recent diplomatic agreements reached in 2024 have unlocked previously classified data that is now guiding the current search operation. Malaysia has negotiated bilateral intelligence sharing agreements with Thailand, Vietnam, and Indonesia that provide access to military radar data previously withheld for security reasons. Australia has declassified satellite tracking information from their defense surveillance systems that reveals additional details about the aircraft's final flight path. These diplomatic breakthroughs represent a fundamental shift in international cooperation on the MH370 investigation, with participating governments finally prioritizing answers over protecting classified capabilities. The comprehensive data sharing now available was impossible during previous search phases due to political and security concerns that have been resolved through careful diplomatic negotiations. Yet even with improved international cooperation and advanced search technology, investigators continue to grapple with physical evidence that defies simple explanations. The debris pieces that have washed ashore across the Indian Ocean over the past 11 years present puzzles that challenge fundamental. The debris trail mystery deepens. 27 confirmed pieces of MH370 debris have been recovered from coastlines across the Indian Ocean, but their locations and timing continue to challenge investigators' understanding of where the aircraft actually crashed. The first major discovery came in July 2015 when a Boeing 777 flatbed washed ashore on Reunion Island, arriving far earlier than drift models had predicted for wreckage originating from the primary search area. This unexpected timing forced investigators to reconsider their assumptions about both the crash location and how debris moves through the complex current systems of the Indian Ocean. Gyro drift analysis based on data from hundreds of tracking buoys revealed that ocean currents between 30 and 35 degrees south latitude could drive fliparan debris to Reunion Island within 16 months of impact. The study showed that currents in the southern Indian Ocean flow east with predominantly westerly winds, while northern currents around 20 degrees south flow westward, creating an intermediate zone with unpredictable movement patterns. These findings suggested that the aircraft might have crashed further north than the original search area, but the complex interaction between multiple current systems made precise location calculations extremely difficult. Marine forensics analysis of barnacle growth on recovered debris pieces has provided investigators with biological evidence about how long wreckage has been in the water and what ocean zones it has passed through. Different barnacle species colonize debris at specific depths and temperature ranges, creating biological signatures that reveal the geographic regions each piece has traveled. The barnacle analysis on the Reunion fliparan indicated exposure to ocean conditions consistent with the southern Indian Ocean search area, but the timing of its arrival suggested that debris movement patterns were more complex than computer models had predicted. 3 additional confirmed MH370 pieces have been recovered from various Indian Ocean locations, each providing investigators with specific manufacturing details that help reconstruct the aircraft's breakup sequence. These pieces include a wing flap section found in Tanzania, an engine cowling piece discovered in South Africa, and a cabin interior panel recovered from Madagascar. The geographic distribution of these confirmed pieces spans thousands of kilometers of coastline, indicating that debris dispersed across a much wider area than originally anticipated. The damage patterns visible on recovered debris pieces have raised questions about the aircraft's final moments that challenge assumptions about how MH370 ended its flight. Some pieces show clean separation along structural joints, while others display twisted metal and stress fractures associated with violent breakup events. The varying degrees of damage suggest that the aircraft may have separated into multiple sections at different times during its final descent, rather than breaking apart simultaneously during a single high-speed impact. Chemical analysis of debris surfaces has revealed exposure to environmental conditions that provide clues about the wreckage's journey through different ocean zones. Spectroscopic analysis of paint degradation and metal corrosion patterns indicates exposure to varying water temperatures and chemical compositions during the debris trail. These chemical signatures help investigators understand the specific ocean environments that debris pieces encountered, providing additional data points for refining drift models and crash location calculations. Advanced forensic techniques now allow investigators to extract information from debris pieces that was impossible to obtain in 2014. Mass spectrometry can identify microscopic particles embedded in debris surfaces that reveal details about the aircraft's final flight conditions. Digital forensics techniques have been applied to electronic components recovered from debris, though saltwater exposure and impact forces have severely limited the recovery of usable data from these systems. The debris distribution patterns have supported new theories about MH370's final flight path that differ from original impact zone calculations. The unexpected early arrival of the fliparan at Reunion Island challenged prevailing drift models and suggested that the crash location might be further north than the primary search area. Physical testing of replica fliparan components in controlled current conditions revealed buoyancy and drift characteristics that weren't fully accounted for in original oceanographic models. Citizen science efforts have transformed debris recovery from a passive process dependent on chance discoveries into an active search network spanning thousands of kilometers of Indian Ocean coastline. Beachcombers from Madagascar to Western Australia actively search for potential aircraft debris using identification guides, reporting protocols developed by aviation investigators. This volunteer network operates through social media platforms and dedicated apps that allow beach walkers to report suspicious debris with GPS coordinates and detailed photographs. The Citizen Science Network has resulted in the recovery of multiple confirmed MH370 debris pieces that would have been missed by conventional search operations. Trained volunteers conduct systematic beach surveys in high-probability areas identified by drift models, while casual beachgoers contribute opportunistic discoveries during recreational activities. This distributed search approach has expanded the effective search area for debris recovery far beyond what professional search teams could cover using traditional methods. Recent debris discoveries have provided investigators with pieces containing serial numbers and manufacturing codes that enable precise identification of their original location on the aircraft. These numbered components allow investigators to reconstruct the sequence of structural failures during breakup and determine which sections of the aircraft separated first during the final descent. The manufacturing data helps investigators develop more accurate models of the aircraft's final moments and refine calculations about the likely crash location. No credible acoustic detections matching MH370's black box emergency beacons were ever confirmed during any search phase, despite extensive underwater listening operations. The Comprehensive Test Ban Treaty Organization analyzed acoustic data from hydrophone networks across the Indian Ocean but found no signals consistent with aircraft emergency locator transmissions. This absence of acoustic evidence has complicated efforts to pinpoint the wreckage location and has forced investigators to rely primarily on debris analysis and satellite data interpretation. The debris trail evidence has fundamentally altered investigators' understanding of MH370's final flight, but the physical wreckage pieces represent only fragments of a much larger puzzle. While marine forensics and drift analysis have provided valuable clues about the aircraft's final moments, the most significant breakthroughs in understanding what happened to MH370 may come from reanalyzing the digital evidence that was captured during the aircraft's final hours of flight. Advanced flight path analysis. The Inmarsat satellite handshake data contains mathematical signatures that reveal MH370's flight path with unprecedented precision when analyzed using modern computational methods. Machine learning algorithms can process the complex relationships between satellite position, aircraft location, and signal characteristics at speeds impossible for human analysts, identifying patterns in the timing and frequency shifts of the satellite transmissions that indicate deliberate navigational changes rather than straight-line flight after radar contact was lost. The satellite handshake system works by measuring the time delay between ground station transmission and aircraft response, combined with Doppler frequency shifts that indicate the aircraft's movement relative to the satellite's position. These measurements create 7 distinct arcs representing possible aircraft positions at specific times throughout the final hours of flight. The 7th arc, derived from the final satellite transmission, has become the primary focus for determining MH370's crash location in the southern Indian Ocean. Inmarsat's analysis of the handshake data revealed that MH370 followed a southern trajectory after its final radar contact, with the aircraft's position calculated using burst timing offset measurements and burst frequency offset analysis. The timing data indicates how long radio signals took to travel between the aircraft and satellite, while frequency analysis reveals the aircraft's speed and direction based on Doppler shift patterns. The ATSB First Principles Review identified a high probability crash zone within approximately 25,000 square kilometers near 35 degrees south latitude. This area extends roughly 25 nautical miles on each side of the 7th arc, from around 32.5 degrees south to 36 degrees south. The refined search area represents the most likely location based on comprehensive analysis of satellite data, aircraft performance parameters, and drift modeling of recovered debris pieces. Machine learning systems have been deployed to rapidly filter sonar contacts during underwater search operations, processing thousands of acoustic signatures to identify potential aircraft debris while eliminating false positives from geological formations and marine life. These algorithms can distinguish between natural seafloor features and manufactured objects by analyzing acoustic reflection patterns, size, characteristics, and geometric shapes that indicate artificial origins rather than natural formations. Fuel consumption. Calculations incorporating detailed weather data from March 8, 2014 have refined estimates of MH370's maximum range and likely crash location Boeing 777 fuel consumption varies significantly based on altitude, airspeed, and atmospheric conditions, with strong headwinds exceeding 100 knots, reducing the aircraft's range by approximately 400 nautical miles compared to standard conditions. The atmospheric data shows jet stream patterns and wind shear that would have affected engine efficiency and optimal flight altitudes throughout the aircraft's final hours. Analysis of the aircraft's gliding capabilities reveals that a Boeing 777 can travel approximately 120 nautical miles after fuel exhaustion when gliding from cruise altitude with both engines failed. However, controlled descent scenarios with partial power optimal pilot technique could extend this range by several hundred nautical miles, expanding the possible crash zone beyond areas calculated based purely on powered flight time. Flight test data from similar aircraft demonstrates that experienced pilots can maintain controlled flight for up to 20 minutes after fuel exhaustion under optimal conditions. Advanced flight simulators recreating the exact conditions from the night of the disappearance have tested thousands of possible flight scenarios based on available satellite data and aircraft performance parameters. These simulations incorporate the specific atmospheric conditions, aircraft weight, and fuel load from March 8, 2014. Allowing investigators to determine which flight path scenarios produce satellite handshake patterns matching the actual inmarsat at transmissions from MH370. The simulator testing reveals that certain combinations of altitude changes and course corrections consistently produce satellite data patterns closely matching the actual transmissions. The most accurate simulations suggest the aircraft maintained cruise altitude for longer periods than previously estimated, affecting fuel consumption calculations and extending the aircraft's possible range beyond initial projections. These scenarios indicate the aircraft remained under active control throughout most of its final flight. Recently released radar data from Thailand and Vietnam has provided additional confirmation of MH370's flight path during the early hours after its disappearance. Thai military radar shows the aircraft's track across the Malay Peninsula with precise timing that confirms normal flight speeds and altitudes during the initial course change. The radar data indicates smooth course corrections rather than erratic patterns that would suggest loss of control or system malfunctions. The comprehensive analysis incorporating satellite data, atmospheric modeling, and radar tracking suggests MH370 remained under pilot control throughout most of its final flight. The evidence points to deliberate course corrections and altitude management consistent with someone actively flying the aircraft until its final moments. The extended flight time and continued pilot input indicate the aircraft may have attempted a controlled water landing rather than experiencing a high-speed crash. Current search operations focus on the southern end of the high-probability area identified in the ATSB review, where drift modeling indicates debris would most likely reach the locations where confirmed MH370 pieces have been recovered. The mathematical precision of satellite handshake analysis has narrowed the search zone to manageable dimensions, but the ocean depths and challenging conditions continue to complicate recovery efforts. The satellite data analysis has provided investigators with the most reliable evidence about MH370's final hours, yet questions remain about the human factors that guided the aircraft along its calculated flight path. Understanding the technical aspects of the flight path represents only part of the investigation, as forensic analysis of other evidence sources continues to reveal additional details about the circumstances surrounding the aircraft's disappearance. Digital forensics analysis of Captain Zahari Ahmad Shah's home flight simulator has revealed data that continues to generate controversy among investigators 11 years after MH370's disappearance. The FBI's examination of the captain's personal computer recovered flight simulator data that had been deleted shortly before the aircraft vanished, including 7 coordinates that closely match the search arcs later used by investigators to define MH370's probable flight path over the Indian Ocean. The recovered simulator data was created approximately 1 month before MH370's disappearance and deleted the day after its creation on February 3, 2014. The flight path found on the simulator included waypoints that terminated in the southern Indian Ocean, in an area consistent with a satellite handshake analysis that later guided search operations. Malaysian authorities initially stated that nothing sinister had been found on the simulator, but the discovery of coordinates matching the aircraft's presumed route raised questions about whether the data represented routine pilot training or something more concerning. Professional pilots routinely use flight simulators to practice unusual scenarios, emergency procedures, and routes they might never encounter during normal operations. Captain Shaw was known to be an aviation enthusiast who spent considerable time using his home simulator to explore different flight scenarios and challenging approaches. The simulator contained hundreds of flight segments covering routine operations, system failures, and navigation challenges that pilots typically practice throughout their careers. The interpretation of flight simulator evidence remains contentious because the presence of specific flight paths doesn't automatically indicate criminal intent. Aviation experts note that pilots often explore theoretical scenarios for educational purposes, testing aircraft performance under various conditions and practicing responses to emergency situations. The statistical significance of finding one route among many possible scenarios becomes a crucial factor in determining whether the simulator data represents evidence of premeditation or coincidental training activity. Investigators conducted extensive analysis to determine whether the recovered flight paths showed patterns consistent with normal pilot training activities or indicated unusual focus on specific scenarios. The examination revealed that Captain Shaw had practiced various emergency procedures, unusual weather scenarios, and challenging airport approaches that represent standard pilot training activities. The comprehensive nature of his simulator usage suggested systematic preparation for unusual scenarios rather than obsessive focus on any particular route. The timing of the data deletion has generated additional scrutiny, as the flight path was removed from the simulator just one day after its creation and approximately 5 weeks before MH370's disappearance. However, investigators noted that routine simulator maintenance and data management could explain the deletion timing, as pilots often clear old flight data to maintain system performance and storage capacity. Comparative analysis with similar aviation incidents provides context for interpreting simulator evidence, though few cases offer direct parallels to the MH370 situation. The Germanwings Flight 9525 incident demonstrated how flight simulator data might reflect premeditation in pilot involved crashes. That case involved clear evidence of mental health issues and deliberate actions that aren't present in the MH370 investigation. The absence of definitive evidence of psychological distress or clear motive in Captain Shaw's case complicates efforts to draw conclusions from the simulator data. Investigators noted unusual behavior patterns in Captain Shaw's activities leading up to the flight, including the absence of social or professional plans scheduled after March 8, 2014. However, this observation must be weighed against the lack of other indicators typically associated with pilot-involved incidents, such as financial problems, relationship difficulties, or documented mental health concerns. The investigation team conducted over 170 interviews but found no clear evidence of personal or professional stressors that might have motivated deliberate action. The broader context of the simulator evidence includes consideration of alternative explanations for MH370's disappearance that don't involve pilot action. Technical malfunctions, cargo-related incidents, or other emergency scenarios could explain the aircraft's deviation from its planned route without requiring deliberate pilot intervention. The presence of 221 kilograms of lithium-ion batteries in the cargo hold has generated particular interest among investigators exploring non-pilot theories for the aircraft's disappearance. Lithium-ion battery incidents have caused serious aviation safety concerns in recent years, with several documented cases of cargo fires and emergency landings attributed to battery malfunctions. The International Civil Aviation Organization implemented new regulations restricting bulk shipments of lithium-ion batteries on passenger aircraft following multiple safety incidents, though these regulations were enacted after MH370's disappearance. The batteries aboard MH370 were reportedly packed according to existing safety standards, but investigators have examined whether battery-related fires could have contributed to the aircraft's emergency situation. The cargo manifest analysis revealed that the lithium batteries were manufactured by Motorola Solutions and were being shipped to Beijing for use in two-way radio systems. The batteries were classified as Class 9 dangerous goods and were properly declared and packaged according to international shipping regulations. However, the potential for thermal runaway events in lithium-ion batteries, even when properly packaged, has led investigators to consider whether cargo compartment fires might have forced the crew to attempt emergency procedures that ultimately led to the aircraft's loss. The simulator evidence controversy illustrates the challenges investigators face when analyzing circumstantial evidence in complex aviation incidents. While the recovered flight data raises questions about the captain's activities before the flight, the evidence remains insufficient to support definitive conclusions about his role in the aircraft's disappearance. The investigation continues to examine multiple theories and evidence sources, seeking technological solutions that might provide more conclusive answers about what happened during MH370's final hours. As investigators grapple with interpreting digital evidence and exploring various theories about MH370's fate, the search for physical wreckage continues with increasingly sophisticated detection methods that promise to break through underwater detection methods. The current search operation relies on proven underwater detection technologies that have been refined through years of deep ocean exploration rather than experimental systems. Side-scan sonar and synthetic aperture sonar represent the backbone of modern underwater search capabilities, with spatial resolution that has improved dramatically since the original MH370 search operations. The 2014-2017 underwater search achieved spatial resolution of 40 to 110 meters using bathymetric survey equipment, while synthetic aperture sonar systems used by the ProSAS deep tow vehicle provided resolution down to 10 centimeters for detecting objects as small as 2 cubic meters. Modern side-scan sonar systems create detailed acoustic images of the seafloor by transmitting sound pulses and analyzing the reflected echoes that bounce back from objects and geological features. The sonar towfish operates at depths up to 6,000 meters while being towed behind surface vessels, scanning wide swaths of seafloor with overlapping coverage patterns that ensure no areas are missed. The acoustic signatures produced by manufactured materials like aircraft aluminum create distinct patterns that differ significantly from natural rock formations and marine sediments. Synthetic aperture sonar technology processes multiple acoustic returns from the same target area to create high-resolution images that reveal fine details of potential wreckage. This technology combines data from multiple sonar pings as the vehicle moves across the search area, using advanced signal processing to enhance image quality and resolution. The synthetic aperture systems can distinguish between objects based on their acoustic reflection properties, identifying metallic surfaces, geometric shapes, and structural arrangements that indicate artificial origins rather than natural seafloor features. Private sector autonomous underwater vehicles like the Bluefin 21 and Hugin 4500 have transformed deep ocean search capabilities through their extended operational endurance and sophisticated sensor packages. The Bluefin 21 can operate autonomously for up to 25 hours while covering search areas of 40 square kilometers per mission. Equipped with side-scan sonar, multi-beam echo sounders, and high-resolution cameras, the Hugin 450 extends operational capabilities to depths of 4,500 meters with mission durations exceeding 50 hours, allowing comprehensive coverage of large search areas without requiring frequent vehicle recovery and redeployment. These autonomous vehicles navigate using inertial navigation systems combined with acoustic positioning beacons that provide precise location tracking throughout their missions. The vehicles follow pre-programmed search patterns while automatically adjusting their altitude above the seafloor to maintain optimal sonar performance despite changing topography. Advanced optical avoidance systems allow the vehicles to navigate safely around underwater terrain features while maintaining systematic coverage of the designated search areas. Bioacoustic monitoring systems complement traditional sonar searches by detecting changes in marine life behavior that might indicate the presence of large artificial structures on the seafloor. Aircraft wreckage creates unique acoustic environments that attract specific species of fish and other marine organisms, generating characteristic sound patterns that can be detected by sensitive hydrophone arrays. Deep-sea creatures often establish territories around large artificial structures, creating biological signatures that persist for years after the initial disturbance. The bioacoustic monitoring process involves deploying networks of underwater microphones that record marine life sounds continuously over extended periods. Advanced signal processing algorithms analyze these recordings to identify changes in species composition, population density, and behavioral patterns that might indicate the presence of aircraft wreckage. The system can detect the distinctive sounds made by fish species that typically colonize artificial structures, as well as changes in the acoustic behavior of marine mammals that might avoid areas with large metallic objects. Machine learning algorithms analyze sonar imagery to distinguish between natural geological features and artificial objects with accuracy rates that have improved substantially since the original search operations. These systems process sonar data in real time, flagging potential targets for human review while filtering out false positives caused by natural seafloor features. The algorithms can detect subtle patterns in sonar returns that indicate the presence of manufactured materials, geometric shapes, and structural arrangements that don't occur naturally in marine environments. Advanced underwater communication systems enable real-time coordination between multiple search vehicles operating at different depths in locations across the search area. Acoustic modem systems provide data transmission capabilities that allow continuous sharing of sensor data, positioning information, and target identification between fleet members. The communication systems use frequency hopping techniques and error correction algorithms to maintain reliable data links despite the challenging acoustic environment of the deep ocean. Specialized recovery tools have been developed specifically for extracting large objects from deep ocean sediment without damaging fragile aircraft components. These tools use controlled water jets and suction systems to carefully remove sediment layers while preserving the integrity of buried objects. The extraction process can remove substantial volumes of sediment while maintaining precise control over the excavation depth and area, ensuring that potential evidence remains intact during recovery operations. The 2025 search operation has identified multiple targets that exhibit characteristics consistent with aircraft wreckage, including magnetic anomalies, geometric shapes, and acoustic signatures that match the expected properties of Boeing 707 components. Each target requires detailed investigation using multiple detection methods to confirm its identity and assess its potential significance to the MH370 investigation. The systematic approach ensures that promising contacts receive thorough examination while maintaining efficient coverage of the broader search area. The technological capabilities now deployed in the search represent the culmination of decades of advancement in underwater exploration, yet the financial resources required to sustain these operations have reached unprecedented levels that challenge the limits of what governments and private companies can reasonably invest in a single aviation investigation. The economic impact of the search. The search for MH370 has consumed more financial resources than any aviation investigation in history, with total expenditures reaching between $135 and $160 million across 11 years of operations. This figure dwarfs the cost of previous major aviation investigations, including the Air France 447 search that cost approximately $40 million and the TWA 800 investigation that required $100 million over 4 years. The MH370 search represents a financial commitment that surpasses the annual budgets of many national aviation safety agencies, reflecting both the scale of the operation and the unprecedented challenges of searching the vast expanses of the southern Indian Ocean. Malaysia bore the initial financial burden during the first months of searching, spending $70 million through February 2016, according to government financial disclosures. The Malaysian Transport Minister revealed that the country's total expenditure reached 500 million Malaysian ringgit, equivalent to $112.47 million by February 2017. Australia assumed a substantial share of search costs when they took operational control of the southern Indian Ocean search area, with the Australian government awarding a $52 million underwater search tender while coordinating multinational search efforts that involved ships and aircraft from more than a dozen countries. The multinational nature of the search operation created complex cost-sharing arrangements that reflected both international aviation law obligations and diplomatic relationships between participating nations. China deployed naval vessels and aircraft worth millions of dollars in operational costs while maintaining search operations in multiple ocean areas for several months. The United States provided satellite analysis, underwater search equipment, and technical expertise that carried substantial operational costs but weren't directly billed to other participating countries. New Zealand, India, Japan, South Korea, Vietnam, and the United Kingdom contributed personnel, equipment, and operational support that collectively added tens of millions of dollars to the total search expenditure. Ocean Infinity's no-find, no-fee contract represents a fundamental shift in how expensive search operations are financed, transferring financial risk from government budgets to private companies willing to invest in advanced technology. The company's $70 million reward agreement for the 2025 search demonstrates how performance-based compensation structures can sustain search efforts when traditional government funding becomes politically or economically unsustainable. This financing model allows continued search operations without requiring sustained government expenditure while incentivizing private sector innovation and underwater exploration capabilities. The development of MH370 specific search technologies has driven innovation across the marine technology sector, creating new expertise and expanding existing businesses focused on underwater exploration capabilities. Advanced sonar manufacturers have developed higher resolution systems capable of operating at greater depths with improved target discrimination. Autonomous vehicle manufacturers have extended operational ranges and improved reliability based on lessons learned from MH370 search operations. Battery technology companies have developed extended life power systems that enable weeks of continuous underwater operation without surface recovery. The search operations have created thousands of jobs across multiple industries, from marine technology specialists to data analysts and logistics coordinators. Australian search coordination efforts employed hundreds of personnel directly while supporting additional employment in marine services, equipment manufacturing, and technical support industries. The expertise developed during MH370 search operations has proven valuable for other underwater exploration projects, including archaeological expeditions, environmental monitoring programs, and commercial deep-sea mining operations. Technical expertise gained from MH370 search operations has enhanced capabilities for locating other missing aircraft and investigating aviation incidents worldwide. The advanced search methodologies, data analysis techniques, and international coordination protocols developed for MH370 have been applied to subsequent aircraft search operations with improved efficiency and success rates. Training programs based on MH370 search experiences have improved emergency response capabilities for aviation authorities across multiple countries. Insurance industry implications from the unresolved MH370 case have created unprecedented challenges for aviation risk assessment and claims processing. Insurance companies have faced substantial payouts for passenger compensation and hull loss claims, while the underlying cause of the disappearance remains undetermined. The lack of definitive accident causation has complicated risk modeling for similar aircraft operations and influenced premium calculations for airlines operating over remote ocean areas. The unresolved nature of the case has prompted aviation insurers to reassess coverage terms for flights over remote areas where search and recovery operations would be extremely expensive. Some insurance policies now include specific provisions for extended search operations and family support costs that weren't considered necessary before the MH370 incident. The financial uncertainty has influenced airline operational decisions about route planning and emergency response capabilities. International aviation safety regulations implemented following the MH370 disappearance have required substantial financial investments from airlines and aviation authorities worldwide. The International Civil Aviation Organization's requirements for enhanced aircraft tracking systems have cost the global aviation industry over $2 billion in equipment upgrades and operational modifications. Airlines have invested in improved emergency locator transmitters, enhanced flight data recording systems, and real-time position reporting capabilities that represent ongoing operational expenses. Regulatory compliance costs extend beyond equipment purchases to include training programs, operational procedure modifications, and ongoing monitoring systems that require sustained financial commitments from aviation operators. The implementation of enhanced tracking requirements has created new business opportunities for aviation technology companies while imposing additional operational costs on airlines that ultimately affect ticket prices and operational profitability. The financial burden on MH370 families has been devastating, with many spending their life savings on private investigators, legal fees, and travel expenses related to their search for answers. Some families have mortgaged homes and depleted retirement savings to fund independent research efforts and maintain legal challenges to government agencies and airlines. The absence of definitive answers has prolonged the financial strain on families who cannot achieve legal closure or settle insurance claims related to their losses. Family advocacy efforts have generated substantial fundraising through crowdfunding campaigns and private donations that have supported independent debris searches and technical consultations. These grassroots funding efforts have raised hundreds of thousands of dollars for family-led research initiatives while demonstrating sustained public interest in finding answers about the disappearance. The economic investment in finding MH370 has reached levels that test the boundaries of what society considers reasonable for a single aviation investigation, yet the potential value of finally obtaining answers extends far beyond the financial calculations that have sustained these efforts for over a decade. What success in 2025 would mean? Finding MH370 in 2025 would represent the conclusion of aviation's most perplexing mystery, and provide answers that 239 families have waited 11 years to receive. The discovery would mark the end of speculation and conspiracy theories that have surrounded the disappearance since March 8, 2014. For the families who have endured more than a decade of uncertainty, false hopes, and unanswered questions, locating the aircraft would provide the concrete evidence they need to begin processing their grief and moving towards some form of closure. The recovery of MH370's flight data recorders would unlock the aircraft's final secrets and provide investigators with precise information about the last hours of flight. These black boxes likely remain intact at the ocean depths, as similar devices have survived decades underwater in previous aviation incidents. The flight data recorder captures hundreds of parameters every second, including airspeed, altitude, heading, engine temperatures, fuel flow rates, and control surface positions. This information would show whether the aircraft experienced mechanical failures, was under pilot control, or encountered other circumstances that led to its disappearance. The cockpit voice recorder would provide crucial evidence by preserving conversations between the flight crew, communications with air traffic control, and any sounds from the cabin or cockpit that might indicate the nature of the emergency. These recordings could reveal whether the crew was responding to system failures, dealing with security threats, or experiencing other situations that affected the aircraft's flight path. The voice recorder might also capture background sounds that indicate decompression, fire, structural failure, or other catastrophic events that could explain the aircraft's disappearance from radar coverage. The discovery would either validate or disprove the numerous theories that have emerged over 11 years of speculation about MH370's fate. Mechanical failure theories would be tested against evidence of system malfunctions, structural damage, or maintenance issues revealed by wreckage analysis. Pilot involvement theories would be evaluated based on flight data recorder information showing control inputs, flight path changes, and cockpit communications. Hijacking scenarios would be assessed based on evidence of security breaches, unauthorized access to cockpit systems, or signs of struggle within the aircraft. Conspiracy theories involving military intervention, cargo-related incidents, or cyber attacks would be examined against physical evidence and flight data recorder information. The discovery will provide concrete facts to replace years of speculation and misinformation that have circulated about the aircraft's disappearance. Aviation safety experts would finally have reliable data to assess the actual risks and develop appropriate countermeasures for preventing similar incidents in the future. For the families of MH370's passengers and crew, finding the aircraft would bring the closure that comes from having definitive answers about what happened to their loved ones. Many families have struggled with the ambiguous loss that comes from not knowing whether their relatives are alive or dead. The discovery would allow them to move forward with funeral arrangements, settle legal matters, and begin the healing process that has been impossible without concrete evidence. Voice 370 and other family advocacy groups have demonstrated remarkable persistence in maintaining pressure for continued search efforts, transforming their grief into organized action that has influenced aviation safety policies worldwide. The emotional impact extends beyond individual families to entire communities that have supported the search effort for over a decade. Chinese families, who comprise 2/3 of the passenger manifest, have maintained vigils and advocacy campaigns that have kept international attention focused on the case. Malaysian families have navigated complex relationships with their government while demanding transparency and continued search efforts. The global community of supporters who have followed the case through social media and citizen science efforts would share in the sense of resolution that comes from finally solving aviation's greatest mystery. Real-time aircraft tracking mandates implemented since MH370's disappearance represent one of the most significant aviation safety improvements of the past decade. The International Civil Aviation Organization now requires aircraft flying over oceanic areas to report their positions at least every 15 minutes when outside radar coverage. These regulations directly address the fundamental problem that allowed MH370 to disappear without trace, ensuring that future aircraft cannot vanish as completely as MH370 did on March 8, 2014. The enhanced tracking requirements have transformed how airlines monitor fleets during oceanic flights, with satellite communication systems providing continuous position updates and emergency alerts. Unavailable in 2014. Airlines have invested billions of dollars in upgraded equipment and monitoring systems that provide real-time awareness of aircraft status and location. These improvements mean that any future aircraft emergency over remote areas would trigger immediate response protocols rather than the hours of confusion that followed MH370's disappearance. Legal implications of finding MH370 would affect multiple ongoing court cases and insurance claims that have remained unresolved due to the lack of definitive evidence about the cause of the aircraft's loss. Families who have filed lawsuits against Malaysia Airlines, Boeing, and other parties would finally have concrete evidence to support or challenge their claims. Insurance companies that have paid claims related to the aircraft's disappearance would have information to assess whether their payouts were appropriate and whether additional coverage issues need to be addressed. The search technologies developed specifically for finding MH370 would benefit investigations of other missing aircraft around the world. The advanced autonomous underwater vehicles, improved sonar systems, and AI-powered analysis tools created for this search could be deployed to locate other aircraft that have disappeared over water. Future aviation accidents over remote areas would benefit from the enhanced search capabilities and international coordination protocols developed during the MH370 search operations. Yet the true measure of success in solving this mystery extends beyond the technical achievements and regulatory improvements that have emerged from 11 years of searching. The persistence demonstrated by families, investigators, and search teams has established precedents that will influence how the aviation industry responds to future crises and how society commits resources to finding answers when aircraft disappear under mysterious circumstances. The financial investment and technological advancement generated by this search have created lasting changes that extend well beyond the MH370 case itself. The mandatory satellite tracking requirements implemented by the International Civil Aviation Organization now ensure that commercial aircraft report their positions every 15 minutes when flying over oceanic areas, directly addressing the fundamental problem that allowed MH370 to vanish without trace. Ocean Infinity's no-fine, no-fee contract model has established a new framework for financing expensive search operations when government resources become politically or economically unsustainable. This private sector approach transfers financial risk while incentivizing technological innovation in underwater exploration capabilities that benefit multiple industries beyond aviation. The 2025 Search Innovations and Families Persistent Advocacy efforts have fundamentally reshaped aviation safety protocols, creating regulatory frameworks and search capabilities that will protect future passengers from experiencing similar uncertainty when air